All right, everyone, welcome back to part 3 of the solid state physics midterm review. So now we're going to talk about photoelectric effect, and the testable questions here are not too bad, so I'm just going to fly through it. So if you have a metal surface and a photon comes in with enough energy uh, to overcome the work function that's required, you can release a electron from its valence band. So a few important concepts. So the equation of relevance here is that for a given frequency of light that shines upon a um, metal, the maximum kinetic energy that the electron can have when it's released is the K max, but it also still has to overcome the work function. So you'll see with this one, and this is a few ways that I've seen students getting tricked. You should be able to know um, that that in order for it to overcome this work function, there's something called a cutoff frequency and a cutoff wavelength. And what I want you to do is pause the video right now and ask yourself, when they say cutoff, are they referring to a minimum or a maximum frequency? And when they say cutoff wavelength, are they referring to a minimum or a maximum wavelength? So pause the video right now and I'll give you 1 second and see if you can get it correct. Okay. So before we answer that question, I'm gonna draw two different light waves. Maybe that's not the best one. Okay, we'll say that's one, and then that's another one. So from looking at this, we can see, obviously, if we call this one 1 and 2, we can see that 1. Okay, sorry. Let's do it like this. We can see that wavelength 1. We can see that wavelength 1 is greater than wavelength 2, right? Because a wavelength is like that, and here the wavelengths are bigger. So what about the frequency though? The frequency of 1 is going to be bigger or larger than frequency of 2. It's going to be smaller than frequency of 2. And most importantly, energy. Which of these two is going to have a higher energy? It's going to be energy of 1 is smaller than energy of 2. Okay, so if you can remember this relationship, you shouldn't get thrown off. So when we're talking about cutoff frequency, we're talking about the minimum energy required. So we need to say that the minimum energy is also going to be related to the minimum frequency, because anything of a higher frequency would meet the criteria, and the maximum wavelength. So you might get thrown off here where they ask you, will wavelengths of this that are bigger or larger or smaller, whatever, and you need to be able to figure out that if it's any smaller, it should work, and if it's any larger, it won't work, and here any smaller of a frequency won't work. So just keep in mind, and both of these are related to the work function here, okay? So let's do one example. So here it says light wave with a wavelength of 413 nanometer strikes a plate with a work function of 1 eV, in contrast to the usual photoelectric effect experiment where electrons are decelerated. These electrons are accelerated across the gap between two plates. If the accelerating voltage of the two plates is 2 volts, what is the kinetic energy of the electrons when they reach the other plate? Okay, so let's take a look. So we have here E is equal to HF. H is Planck's constant, but we also can say this as HC over wavelength, and HC here we have a convenient short form for it, and that's 1240 eV nanometers. Okay, so 1240 eV nanometers, and this is in the formula sheet, divided by 13 nanometers. Okay. I can't remember actually if this is supposed to be 413 or 431, but let me just pause. Can I pause the recording here? Let's see. No, I can't. Okay. Let me just real quick. Okay. Yeah, it should be 413. So here we get is equal to 3 eV. And from there, sorry about that. From there, we know that, so that's the energy of the light that's initially coming in. But for photoelectric effect, we know that the energy is going to be K max plus the work function. The energy it comes in with is 3 eV. So that's going to be K max. And the work function plus 1 eV. So the maximum kinetic energy that those electrons can have when they're released is 2 eV. And then because there's a 2 volt accelerating voltage between the two plates, and we want to know what happens when it reaches to the other side, the kinetic energy final will be equal to the was going to be equal to the initial plus the accelerating voltage, so 2 eV plus, and because it's 2 volts, right? It's 2 volts, the difference between, so this could be 2 and 0 volts, right? So plus on this side, minus on this side. So because it's 2 volts, but we're talking about a photoelectron, we can say that this is 2 eV. So our answer is 4 eV. Okay. So that's the end for photoelectric effect. And I'll see you in the next one where we discuss Hall voltage.